Okay, section 11.4, reverse chain rule. We are going to do this section by using substitution. So here I've written my advice is to still use the substitution method, even though the book does it by applying reverse of chain rule and you spotting the patterns. But I would always replace the awkward bit with a substitution, and so the inside function, that's normally, or if there seems to be two brackets, the bracket that gets higher power or more awkward power. Okay, so we are going to use substitution. So over here we've got 2x over x squared plus 1. So the denominator, if it's a fraction, you always should try to replace the denominator. If you were to bring this bracket to the top, that's the one that will be getting the power of -1, awkward power. So normally we use letter u, but you also need to be able to use a different letter in case you already have u in the question. So u is equal to x squared plus 1. So I'm interested in replacing this first of all. As soon as you decide on your substitution, you need to differentiate it. So these two steps are crucial. So that is going to be 2x. And here we're going to do something that's a little bit strange, because we're going to treat du dx as if it was a fraction. So you're going to separate these, multiply it by dx if you like, but it's not really the case. And then what we are going to do, we are going to start substituting. Some people carry on. I like to pause here and then see, have I got 2x dx? And you see, I have got 2x dx. So I can see that I've got the substitution for 2x dx. That will be du. But some people carry on and then they do dx, because they know they have to replace dx. And that can be replaced with du over 2x, and then they substitute du over 2x into this, and that 2x will cancel. But I like to do hesitate. It doesn't always work out nicely, but over here I'm looking for what I've got already, and I can see that this here, that will be du. Now x squared plus 1, that's going to be substituted with u. So I've got du over u, or you could write it as 1 over u du, and that goes to ln u plus c. But u is x squared plus 1, so it's ln x squared plus 1 plus c. I don't need modulus signs here anymore, because x squared plus 1 is always positive, and this is why those modulus are placed there, to keep the expression positive. Okay, so over here we've got another expression, another fraction. If you look in the denominator, that's the bit you'll be bringing to the top and giving it power of -1. So I'm going to replace the denominator with u. So as soon as you've decided on your substitution, differentiate that. So that 3 goes to 0, 2 sine x goes to 2 cos x. So du is equal to 2 cos x dx. Now I like to stop here to see whether I've got 2 cos x dx. Now I haven't got 2 cos x dx, but I've got 1 cos x dx. So 1 cos x dx can be replaced with half du. So let's do that. So this one is going to be a half du, and this is going to go to u, but you have 1 over u times a half du. Integrate it, you can take the half out, and then ln will go to ln modulus of u. And then let's go back to our substitution. Always go back to x's in those questions. 3 plus 2 sine x plus c. And there is your answer. Okay, let's move on to example 9. So in the example 9, you've got product of two functions. You've got 3 cos x times sine squared x. So I'm going to substitute for the one that gets a higher power. But you also will begin to realize that sine differentiates to cos. So you always want to keep the derivative and you want to replace the function that was differentiated, because remember, integrating is the opposite of differentiating. So you're just thinking, what has happened here? What was differentiated to give you that answer? So we're going to replace sine x with u. So du dx is cos x. And here I'm going to do the separating. You've got cos x dx. Now have a little glance at the question above. Have I got cos x dx? And yes, I do. And so that is going to be worth to u. So we're actually ready to do the substituting. So I for the integral is equal to 3 cos x and dx will become du, and sine squared x will become u squared. So we are going to add 1 to the power, divide by that power. So it's going to be 3 over 3 u cubed, which is u cubed. So it's sine cubed x plus c. It's always a good idea to check whether you got the right answer by differentiating it. So if you differentiate, you've got 3 sine squared x times what sine differentiates to, and yes, that's right. Question example 9 part B. Okay, again the same principle follows. If you could see, you've got x and then you've got x squared plus 5, but that's the one that you've got the power of 3. Of course you could expand the power of 3 brackets, or do binomial expansion, but that would be a little bit tedious. So, and you've been asked to use substitution. Well, no, you haven't been asked to use substitution, but sometimes you are. So you just ask to integrate it. So substitute just this bracket. Don't bother with the power. Let's just do the bracket. So du, and it's important to write it as du dx, not just u dash. Okay, so du is going to be 2x dx. So this is where I'm going to stop. And I look for 2x dx. Well, I've got 1x dx. So I've got a half of that answer. So I can replace the underlined parts with a half du. So my integral is going to be, let's put a half du over here. And then this one is going to be u to the power of 3. So I've got a half of u cubed du. Add 1 to the power, divide by that power. So it's a half times u to the power of 4 over 4, which is 1/8. And u to the power of 4 is x squared plus 5 to the power of 4 plus c. And there's your answer. Okay, so we'll just have 2 more examples, and then we're going to do exercise 11D, and I really want you to use the substitution method to solve 11D. Okay, so over here again you have got a fraction, and you could see that if you were to bring it to the top, the denominator would get a awkward power of -2. Power of -2 is more awkward than cosec squared. Another way that you can start thinking, you want to keep the derivative, and 2 plus cot x, that will go to minus cosec squared x. Okay, so I want to keep the derivative. I want to replace the denominator, or what the function would, the function that would differentiate to give you that derivative. So I didn't need the brackets, but never mind. Du dx. So cot differentiates to minus cosec squared x. So du is equal to minus cosec squared x dx. And then you have a look. Have I got minus cosec x dx? Well, I've got a plus. So that must be replaced with minus du. There you go. So let's replace the purple bit with minus du, the bottom bit with u squared, and you will have the integral. It's going to be 1 over u squared times minus du. Let's take that minus in front, and then bring the minus u to the power of 2 to the top, so u to the power of -2. Add 1 to the power, divide by that power. So it's going to be u to the power of -1 over -1 du and here clearly those cancel to give you 1 over u plus c. I do apologize, don't have the u once you've integrated. So this is going to be 1 over 2 plus cot x. Okay, example 11. Let me just separate it a little bit so it's not, I'll do it like this in case we need more space. Oh, okay, so because we will be solving. So in order to solve this equation, and it's nice to actually be introduced to some limits, let's find this integral first of all. So let's do that first. There you go. And over here, I could see that sec differentiates to sec tan. So I want to keep the derivative. So I want to keep tan and 1 of the sec. So I'm going to still go for replacing the weird powers. So this one over here. So let u is equal to sec x. So du dx is equal to sec x tan x. If you differentiate sec, separate du from dx, temporary. You might need to carry on if it doesn't work out, but always stop at this point. Otherwise, you would make dx the subject and then do the substituting. Okay, so sec tan x, have I got it? Well, I do, because if I write this as 5 and take one of those sec, so sec x tan x, and then followed by sec cubed, you could see that I've got sec tan x dx, and that could be replaced with straightforward du. And then this one here is going to be u cubed, and then you've got 5 here, so it's going to be 5 u cubed du. Another common mistake students make, they actually do all this work and then forget to integrate it. So don't forget to integrate it. Add 1 to the power, divide by that power. So it's going to be 5 quarters sec to the power 4 x plus c. We don't need plus c really, because this was only to work out that left-hand side, not yet, because it's a definite integral, so we need to substitute the limits into this answer. So this is the left-hand side of this equation, and that is going to be 5 quarters of sec to the power 4 theta minus sec to the power 4 of 0. Okay, now sec 0, remember sec 0 is 1 over cos 0, and that's 1 over 1, which is 1. And this you have to leave it as sec to the power 4 theta minus 1. So that replaces our left-hand side of the equation. So let's substitute that back into this equation. We'll expand the bracket, make it equal to 15 quarters. So sec to the power of 4 theta is equal to, let's put 5 quarters here. So we're going to add 5 quarters, so it's 20 over 4. So sec is equal to sec to the power of 4 theta. 20, if you divide by 5 quarters, you're going to get 4. So sec squared, square rooted twice, square rooted once, it's plus or minus 2, but you can't have something squared equal to negative, so you only use the positive 2. So sec theta is equal to plus or minus 1 over, plus or minus root 2. That gives me 1 over cos theta equal to plus or minus 1 over root 2. I haven't flipped it yet, so root 2 cos theta, now it's equal to plus or minus 1 over root 2. So from this you could solve, we are solving, I believe, it doesn't say, okay, we are solving, oh yes, it does say here, we are in radians and we only want to find the solution between 0 and pi over 2. Now between 0 and pi over 2, cos theta is positive, so we're only solving cos theta equal to 1 over root 2, so theta is equal to pi over 4. So we don't need to worry about the negative solution. So this leads us to exercise 11D.